remind me. I will try to kind of stop midway so that you can, you can get time to kind of look at notes and take a break. And so let's quickly go over some of the course details. Yeah, as I said, you can reach out to me always on email, and I will have 2 weekly office hours. Basically, after the lecture, I'll just be available in my office to meet. Okay, so and it's pretty informal. You can walk in, you can ask questions about the homework, you can ask questions about anything else you would like about the course. And in case you want more time and you want to meet separately, please feel free to email me. I'm pretty prompt on emails. I try to reply as fast as I can, and we can, kind of meet separately as well. So I'll have 2 office hours every week, and these will be informal. You don't have to set up a meeting, and you can just walk in and we can chat. And I just sit on the same floor and as this room, so it's pretty easy. There are 2 makeup lectures. Unfortunately, I have to travel due to 2 conferences, which we have mentioned. So I've already mentioned. I realize some of you may have a conflict at this time. In case there is a conflict, don't worry, we will have the recordings uploaded, and again, I'll be available to meet if you want to clarify any questions. All right. One of the classes is in November, and the one is in a couple of weeks. So just make sure, and both the lectures will be in this room. Other than that, it will be Monday, Wednesday. There are 3 cancellations in total for lectures that are again mentioned in the course schedule. I will show them in a minute. But essentially, these will be the 2 makeup lectures. Rest everything will go, according to plan. We have one TA, Felipe Henrique, who is at the back. Felipe will be holding his office hours every week, and an additional office hours 1 day prior to homework, which we will talk about in a minute. All right. It'll be room B331. Maybe I think it's incorrectly mentioned hybrid. Will just be a room B331. If we have to change the room, we'll update you in advance. Okay. The required text for the course is this book by William Dean. This is 2nd edition. I highly recommend this book. Some students prefer to not purchase it. It's your choice at the end, but I would say from what I've seen, most students really prefer to have the book. We go through the book quite rigorously with each section, as you will see. I also think it's a good book to just keep as a reference. So I bought this book 10 years back when I was a graduate student, and I still have it. And I use it very often. Even if it's not for your own research, you will just find it as a handy reference to keep it. Okay. There's a BSL, which some of you may have seen in your undergrad, but Stuart Lightfoot, that's just an optional text in case somebody prefers to read in a different writing style. In terms of grading, we will have 3 exams. This is slightly different than your other core courses. So we'll have 3 exams, as I mentioned, 25% each. The first exam is on September 27th. The second exam is October 31st. And final exam will announce. The exams are not cumulative. So we'll have 3 parts of the course, as I will mention several times today. There are very natural breakups in the course. So first part, first exam, second part, second exam, third part, third exam. So we'll not try to have a cumulative exam. And the intention is to make sure that we don't, make a final exam to be the most heavier in terms of weightage. So you have to kind of perform regularly in the class. That's by design. And the last 2 times I've taught the course, students have really appreciated that it's actually regularly spaced out. So keep it that way. There will be 6 problem sets. I will go through them in a bit, but basically bi-weekly, assuming bi-weekly, there will be no homework due during the week of the exam. So there will be 2 homework, every 2 weeks you'll have a homework, except the week of the exams. So 6 problem sets, 20% in total. We will use Gradescope to submit the homeworks. And I think most of you had signed up for the Gradescope. In case, again, there are questions, feel free to reach out to us. We can add you into the course if you haven't used Gradescope before. Finally, this is a new attempt, and I really want to kind of try to encourage this, is using iClickers to kind of have some participation. You will not be graded on this. You just have to come and participate. You can give, whatever answers at that point you feel like. And I will try to keep a sort of a participatory tone in the class. And so these will be 5%. We realize because we have made up the lectures and we have a couple of makeup lectures. So makeup lectures won't be counted in case you have a conflict. And we will also drop 3 days in case you have, some other commitment. So we'll not count them towards your 5%. Okay. So basically you just have to show up to the class, participate in the polls, and you'll get those 5% points automatically. Okay. Any questions at this point about the course, lectures, office hours? Yeah, please.
Sorry, the makeup lectures for the Monday or the
So I'll just talk about that in a second. Yeah, good question. I'll talk about that in a second. Any other questions for that? All right, so let's me answer that question. So this is basically the schedule. We'll follow it as much as possible. I try to kind of not deviate from the topics. So as you can see, we're following the chapters in D on the right column. You can see 1 and 2, 3 and 4 and so on very, very rigorously. And essentially you will see sort of like the dates and when I'm away and when we have the makeup lectures. So the first lecture when I'll be away is the Wednesday, which is 8/31st. And then I'm away for 2 dates on the 14th and 16th of November due to the AKI conference that some of you will be familiar with. So that's Friday we'll have a makeup. Okay, so those are the 2 dates I'll be missing. Now let me just briefly mention again these 3 parts. So you see there is an in-class exam and an in-class exam. So the 3 portions of the courses are naturally divided. The first portion of the course will focus on diffusive transport. Okay, so that's like diffusive transport, heat conduction, and mass transfer. So that will end in the first part. The second part is fluid mechanics. That's like fluid flow. That is what we focus on the second part. And the third part will combine the 2 topics and do like diffusion plus fluid flow. Okay, so transport with both convection and diffusion. So the kind of the natural break is there in the course. So that's why we keep it in 3 separate parts. And feel free to reach out to us if you have any questions about that. And we must have given some details about when the homeworks are due and so on. Okay, and before exams we'll post in practice homework that's not for grade, and we'll also post last year's exams so that you can practice on the solutions. Okay, any questions? And everything will be updated on Canvas regularly. We'll also post some supplementary videos which are basically just I'll sit down and record some lectures, record some videos which are supplementary. That's just to aid your learning. They are not required. And I may also recycle some from the previous years which I have accumulated. So there might be some 20 or so supplementary videos ranging from 5 minutes to 15 minutes. And I do that purposefully because some of the mathematical derivations in the course can run long. And I don't want you to be worried about writing down the maths during the lecture. Okay, so we'll focus a lot more on concepts, and the mathematical details, some of that will be in supplementary videos. Okay, any questions at this point? Anything you want to discuss about the course details and everything structure as well? Okay, so let's now start with why we want to study transport phenomena, and then I'll go towards learning goals and so on. So just so that you know, like my research is entirely on transport phenomena driven. So obviously I'm biased towards this topic, but I do believe that many of you will benefit from your own research, whether you're doing experiments, whether you're doing experiments in bio or catalysis or energy storage or whatnot. Transport phenomena is a very important part of chemical engineering education. And more broadly, like it is also seen in civil engineering, mechanical engineering, aerospace engineering. So it's a very important subject. And there are a lot of probably traditional applications you might have seen in your courses, previous undergrad courses, such as designing heat exchangers, designing distillation columns, and so on. But there is a lot of modern applications of transport phenomena, and I really want to instill that in your course is that you can use the principles we learned in modern applications. So the most important application for today's times is COVID research. And if you have kind of kept track of COVID research, there have been like numerous studies, even from our university, which focus on fluid mechanics of indoor air transport. So in this room we are sitting, ventilation is a key principle. And there has been a lot of research in showing how hospitals should improve ventilation, because that's where the patients are at risk for COVID the most. And ventilation has been shown to be very effective. The other part is that there have been a lot of research on singing in indoor orchestras and in operas. You can see a lot of singing inside the room, which can create which can increase the viral load. So I'll show you a video, which is an experiment on the top. It's a person sort of talking or singing maybe, which shows you the flow patterns, and the bottom part is a simulation trying to capture those details in the system. So this is a pure transport phenomena problem. We're trying to understand the flow patterns, the concentration of a viral load and so on, and that can help you understand how to improve disease transmission within the room. Okay, so this kind of really took off during COVID times, and we still are living through it. And it is a key sort of a design part which came to that indoor for reducing indoor transmission. Ventilation is a key principle. Just to also elaborate on this a little bit more, there was this nice article that came almost 2 years back in lockdown, New York Times. Maybe it's a little hard to see, but hopefully you can see on that screen is some few people standing apart from each other showing how droplets will fall. So you remember the 6 feet rule, which was very, in the initial part of lockdown, that came from the sort of calculations of how the droplets will travel when you speak and sing and so on. Okay. So just again, this is all transport phenomena, fluid mechanics, and so on. And there have been many follow-up studies, and they keep coming in popular press as well. Now let's switch gears. So this is health and diagnostics and so on. There's also like energy storage and environmental stuff. So energy storage also has a lot of transport phenomena. It's also kind of important for my own research. My group works on sort of transport phenomena in batteries, supercapacitors, and so on. And a 2019 report from the Guardian newspaper kind of termed like this age as an iron age. Everything is being electrified. We have electric vehicles. We have everything becoming electric. You have your house, you'll have a solar energy which is being stored through sort of batteries and so on. So basically, this is going to be an iron age where iron transport is going to be increasingly important. And we will talk about iron transport towards the third part of the course, where I try to introduce you what are the tools required to understand iron transport. Okay. From an environmental perspective, there is again increasing interest in trying to clean waters. There is desalination applications, Faraday desalination, which is trying to remove heavy metals and so on. There also, this is important. So this actually figures from Professor Mike Tony's group, who have written a review article on sort of capacity deionization. So I took this image from there. All right. Moving on, we also have stuff like fluid porous media. So as oil is becoming increasingly less and less accessible, we still rely on it as we are transitioning towards. There's also interest in understanding how we can extract the remaining oil. So again, it looks like a pretty mature field, but it's an active area of research. So that what I will show you is different flow patterns. So these are 3 different flow patterns that can happen. And these are simulations actually. I've also verified experimentally, by the way, where you see different flow patterns emerging. In the second case, you see more like uniform spreading. Third, you see more irregular and sort of different kind of spreading features that can happen in a porous media when you're trying to kind of push oil out or water out from a porous media. Again, this is classic transport phenomena. We'll read some of these equations, not again in detail, but some of these equations in the second part of the course. We'll basically learn about wetting and so on. All right. Finally, I like to end with sort of kind of combining heat and mass transfer and so on, which is carbon sequestration. So what you will see here is sort of these sort of patterns that will form because of density separation. This is carbon dioxide being dissolved, and you can see this heavy separation coming out. And you get these really beautiful flow patterns coming out from this, which can, which is again an active area of research. There's also a simulation, by the way. This simulation, this is just a MATLAB code that I wrote up to kind of mimic some of this process that you saw. So these are not complicated things. Again, you'll learn a lot of these things in the class itself. Okay. I haven't written some of the other applications that we covered in the course. Cell membranes and so on also have a transport phenomena. Lungs have a transport phenomena. A lot of biological applications, because I know some of you will be doing research there also have transport phenomena. It's very important. Catalysis, you'll have gas diffusion and so on. So again, transport phenomena, whatever you will learn in this course is going to play a role in your research. I'll try my best to kind of give you examples of how you can use it. Okay, and you're always welcome to contact me for any other questions that you may have, or this topic can apply to your course. All right. With that, let's start with some learning goals, which I think would be helpful now. So in this course, what I really want all of you to kind of learn, take away from the course, is one of the key factors that I've seen is generally not emphasized enough, is that what you really want to be able to do is set up a transport problem. Set up a transport problem. And what does setting up a transport problem contain? That is governing equations, boundary conditions, and initial conditions. Okay, so governing equations, boundary conditions, and initial conditions This is setting up a transport problem, and then you will learn a little bit about how to solve these equations. But I want to really emphasize that the first part is the more important part. Okay. Often I have seen students get lost in the second part is how to solve it. But believe me that this is the first part which is the most important. Sometimes, console and a lot of numerical solvers out there, students do not put enough emphasis on how to set up a transfer problem. So you don't want to set up the most complicated transfer problem. You want to reduce the problem into an effective equation, effective boundary condition, effective initial condition, so that you can solve it in the most efficient form. And I'll try to kind of really come back to this again and again during the course, is that these three steps will happen in the three parts of the course. What is the governing equation? Why is it the correct governing equation? What are the assumptions behind it? What are the correct boundary conditions and what are the correct initial conditions? If you can do that, 80% of the transport is solved. You can solve them. There are enough numerical approaches, analytical approaches to solve them. It's really this, the beauty of transport problem lies in the left part. How to do that. So that's really the learning goal. And I'll emphasize that during the course, that please try to make sure that you take away from this course how to set up the problems correctly, how to really reason out what are the correct governing equations, boundary conditions, initial conditions. Okay. So that is essentially what we will do. And I'll continue to come back to this again. All right. So for today, what I want to do, focus today on just introduce some of this topics of transport. So let's start with what we will do today. So agenda for today is introduce heat conduction and species diffusion. So start to learn, try to understand how we can kind of put down in some sort of equations the process of heat conduction and species diffusion. Okay. And this is chapter 1 of Dean. If somebody wants to also like to read the book, this will be in chapter 1 of Dean. You can look through these topics in Dean itself. And how do we kind of express and start to think about transport? So some of you might have seen this topic before. So maybe a repetition for some of you, and some of you may not have seen this topic before. But to visualize, it's good to visualize of how to think about heat conduction. So let's start with heat conduction first. We'll first focus on heat conduction. And think of this in your mind. You can imagine this book as an iron, some sort of a material of iron. Just think of this as some sort of an iron rod. And let's start to kind of mathematically write what heat conduction might look like. So let's imagine an iron rod. Let's see, this is X direction. This is T1. This is T2. And let's say T2 is greater than T1. So temperature is higher in the second part, right part of the rod compared to the left part of the rod. So which direction do you think the heat will flow? Now, it's a trivial question for some of you, but let's start there. So what direction? Plus X or minus X? Minus X, okay? Because the temperature, the heat will flow from left to right, because it will go from higher temperature to lower temperature. Great. So why is that important? Is because we typically define heat conduction in terms of an energy flux, Q, right? So bar below. So some of you may not be as comfortable with some of these mathematical terminologies. Don't worry, we'll pick them up as the course goes along, and you'll also see some of this in your math methods course. So there'll be some synergy there. So by bar, under bar, I will represent this as a vector minus K grad T. Okay, and the minus here is represented because the heat will flow from higher temperature to lower temperature. That's why there's a negative sign there. Q is a vector. This is a K here is the, sorry, let me just first determine what Q is. This is the heat flux. Heat flux. Okay. And the units of heat flux are energy, joule, per unit area, per unit time. Okay. So the units are joule per meter square second. This K is thermal conductivity, which is a property of the material, thermal conductivity. This gradient of T, or let's first focus on gradient. Gradient, that's an operator del by del x of Ex plus del by del y of Ey. And don't worry, I'll explain what these mathematical operators are. Del by del z of Ez. Okay. So how many of you have seen the gradient operator before? Okay, so hopefully the math method goes in that way. So gradient operator is basically three different derivatives, Ex, Ey, and Ez, where Ex, Ey, and Ez are the unit vectors. Okay, unit vectors. Easy. Okay, and we'll do some examples today so that you will become comfortable with it if you are not already. This is essentially what gives you the. And why do I need a gradient? Because you need a temperature difference to have the heat flux. If T1 and T2 are equal, you know there will be no heat flux, right? So you need a difference, and that's why you have derivatives. Derivatives is a difference. You need these differences to get to the gradient of this. And what is this law called? Some of you may have seen this. It's called Fourier's law. Okay, so this heat conduction law is called Fourier's law. Fourier's law. And I should mention, and presume this is clear, but this T is temperature. This is temperature, and the units are Kelvin. Okay. So any questions on Fourier's law? Anything that's confusing or that you want to clarify? Good. So I want to emphasize that heat flux is a vector. It has a both magnitude and a direction. Okay? And I'll come to this point again. Don't forget that there is always a direction associated with heat flux on top of magnitude, and that direction can be calculated by calculating the division correct. All right. So at this point, just so that we can start to have some participation, let's try to estimate the units. This is pretty simple. Let's try to have the units of the thermal conductivity K. And let me open a poll. Hopefully, you should be able to see this. So that I don't really know if this should work. Are you all able to see this on your phones or no? No, not yet. Okay, let me just see if this is not working. Let's go here. Let's start the class. Do you see it now? No. There's no question there. I hope I'm not making a mistake. All right, must be some error from my side. Just give me 1 second. I'm a little surprised it's not working. Let me start from here. Hopefully this should work. All right, so I do see that you are present, many of you, but for some reason it's not allowing me to start the poll. Right. Nothing after that. Okay. Let's try once more. Hopefully, multiple choice. Anything on the app? Okay, we'll figure it out next class. Don't worry about it. Seems like something is wrong at my end. So I'll just end it for today, and we anyway have everyone who has joined. So let's do this. So what are the dimensions of thermal conductivity K? Hopefully some of you have had the time to look at it. Let's take another 20 seconds to make sure everybody has tried this, and then we'll proceed from there. All right, so now I want you to kind of turn to your neighbor and tell them what answer you wrote and discuss with them if your answers agree. And then, we'll discuss that. Okay? And I may just randomly start to, ask what you have. All right. How many of you changed your answer after talking to your neighbor? Did anybody change their answer after talking to your neighbor? Okay. Anybody else did? Okay. So anybody for answer A? Anybody who was A? So we have a few people with A. Anybody for B? A few people with B. Anybody for C? Not going. So all right. So most of you have the idea correct. The correct answer is B, and it's a small subtlety that the gradient also has a unit. The unit of the gradient is meter inverse. So let's try to do this once more just to make sure. And again, this is just participatory to get you thinking. So, so lecture 1, question 1. The correct answer is B. The units are joule per meter square second here. We want the units of K. The units of gradient are meter inverse, and the units of temperature are are Kelvin. And that's why the K will have joule per meter second Kelvin, and joule per second is watt per meter Kelvin. Okay. So don't forget that the units, they are also the units of gradient, which is why they're one of the meter squares at first cancel to meters. Okay. All right. So with that, now let's start take an example. So I want to start now. We thought of a iron rod, which had this X, we had T1, we had T2. Now let's say we have been given a temperature profile. In later parts of the course, we will be calculating what a temperature profile is, but let's, for illustrative purposes, let's say the temperature of the rod is T2 minus T1 into X by L plus T1, okay? And this is X is equal to 0, this is X is equal to L, so the length of the rod is L, okay? So let's say the temperature of the temperature profile is linear, okay? And now calculate the heat flux. So I want all of you to just maybe take a few seconds, calculate Q vector. Okay, so what is the Q vector here? Calculate that, and then we'll proceed. Take a second to do that. What's the heat flux? All right, I hope some of you did try this. So let's do it together now. So Q vector we have seen is minus K grad T, which means it's minus K del T by del X EX plus del T by del Y EY plus del T by del Z EZ. Temperature T is not a function of Y and Z, so this goes away. So you only have minus K del T by del X EX. And if I take the derivative with respect to X for T of X, we get minus K into T2 minus T1 by L P of x. Okay, so simply that. And does that agree with our expectations of the direction? So note that there is also a direction, right? I mentioned heat flux will always have a direction. So we all said when temperature T2 is greater than T1, I should expect the flux to be the negative. Right? It makes sense that if temperature T2 is greater than T1, this K into T2 minus T1 by L is positive and has a flux is in the negative x direction. If it was the opposite, if temperature T1 was greater than T2, then I'll get a negative here and a negative here will become positive, which would mean that the heat flux is going in the positive x direction. Okay, so this is a very simple example of showing how to take a gradient, how to get the heat flux. Okay, in your first homework, you will see we'll have a much more complex function of temperature, but the idea is the same. Okay, so now let's try to make a little bit more complex temperature profile. And then we will do a similar exercise. So let's do that. That's the second question for the class today. So the temperature profile is given on top. Now it's a function of both x and y. Okay. And we have been given a region, x square plus y square is less than 0 to r square. And temperature T2 is still greater than T1. So find the value of flux. Just do that. And then, I can give you about a minute to do this. So I'll just stop in a minute and then we will do that. Let's discuss this out. All right, maybe this is good enough. Hopefully, if we had the poll working, you would enter your answers. But nonetheless, please talk to a different neighbor now. So you must have spoken to some other neighbor. Please talk to a different neighbor, share your answers, and see if you can come to a conclusion. All right, let's end the discussion. Anybody wants to volunteer this time on what they got as the answer? Anybody wants to explain what they got the answer? Anybody else got C? Many of you got C. And the C is the correct answer. Just so that you all see, even without solving, you can rule out option B because it doesn't have the correct units. Okay, so just so that you can have it in practice. As you can see, the second option, there is a length unit here and a length unit here at R, but you will always have flux to be K temperature difference by units of length. So it's a K grad T. But in the second option B, you have the units sort of cancel out. So B cannot be the answer. It's either A or C, and because of the dependence in x squared, it cannot be A. It has to be some dependent on x. It's C. But that's just like physical argument. Let's try to do it more precisely mathematically. So the correct answer is C, and let's try to arrive at the answer. Okay. So we have this temperature profile. q vector is minus k grad t, which is minus k into del by del x of t ex plus del t by del y of Vy as the flux. And now note T1 is a constant. T1 is not a function of x or y, so it's a constant. It will go away. Now I have this term here, which I have to differentiate because this term doesn't really matter, right? T1 is constant. So when you take a derivative, the T1 will drop out. Now, when I take a derivative with respect to x, the only dependence with respect to x is this part, right? Everything else is a constant. So I will say this is minus k into T2 minus T1 by r square into 2x ex, right? Similarly, I will do T2 minus T1 into y by r square ey. Okay. So when you take common factors out, it becomes minus 2k into T2 minus T1 by r square into x ex plus y ey. Okay. Does it make sense? Anybody has questions here? Don't hesitate to ask questions if you have any questions about this step. I hope you can see now it's two directions. There's a magnitude, but there is also a direction. It's like both x and y. Okay? And if I want to get the magnitudes, I'll just square the x component and the y component, add them and take a square root, right? Remember, if you want to calculate let's say if q vector is qx ex plus qy ey plus qz ez, three parts. If the mod of q would be qx square plus qy square plus q square. Okay, so let's remember that. You can also calculate the magnitude, but clearly the direction has both x and y. Okay. Any questions here for the flux? Yes, please. Exactly. That's where I'm going next. So great question is, how do we understand this result more geometrically? Okay. So let's go back to the question. So if you see it says x square plus y square is less than 0 to r squared. What is this equation for? What do you think is the limit? So we had a solid rod, right? 0 to L, just a straight rod. Now what is the shape of this solid object? Circle, right? It's like a disc, right? So if we are not talking about the third dimension, there may be a third dimension, but for now, let's think of it as a disc. So good observation, everyone. So we have a disc here. All right. So it says x here, y here, and we are always smaller than this radius r. So it's a circular disc of radius r. And just to remind everyone, the t of x comma y was t1 plus t2 minus t1 into x square plus y square by r square. Okay. I believe that is correct. Yes. And so what is the temperature at the center? T1, right? And what is, because at center, x is equal to 0, y is equal to 0, right? So you just substitute that value, you get a center. At the center temperature is T1. And what's the temperature at the outside, like this ring, at the boundary of this disk? T2, right? Because x square plus y square is equal to r square. So you just have r square get cancelled, and you have T1 plus T2 minus T1. So it becomes T2. So temperature here is T2. Now we have been given that T2 is greater than T1. So the outside boundary of the disk is at a higher temperature than the center of the disk. So the flux will go inwards. Right? So everything the flux will go inwards. Now, so this is basically what's going on in this problem. The next question is, as was being asked just now, how do we think about flux now? So it's clearly, if it's radially coming inwards, it has both x and y components, right? And I'm not introducing any radial coordinates right now. Let's just fix the x and y coordinates. Now I ask a question, and this is a question for all of you. What would happen if I take a slice of line like this? So let me maybe sketch it a little bit more clearly. We have a circle here. We have y, we have x. Somehow I sketch a line, this red line here, okay, which has the equation x plus y is equal to r. This is equation x plus y is equal to r, and that's like almost like a line to that. It's passing through 0 comma r and r comma 0. Okay, so that's like it's kind of like a straight line. And now the question is, what is the flux with this line? That's the question I want to. So I want to go a little bit more into the depth of understanding this x and y dependence. So I'm just making this question up that, okay, well, I construct this line, x plus y is equal to r. What is the flux through that line? Okay. So to understand this is a critical point we have to kind of physically understand. So when I think of the flux through a line or through a plane or through a surface, what do you think the direction of that flux should be? Normal to the line. Does everybody see that? I don't really care if the flux is going parallel to the surface. I really just care about the flux going perpendicular to the surface, right? So if you're thinking about flux through a surface, I have to think about the normal direction to that surface, because it doesn't matter if I'm thinking of heat going in this direction. It really just matters to me this, it should be perpendicular to this plane, right? I don't really care if the heat is going, if this is the plane. If the heat is going this to the direction, it's not going to go through that plane. So it has to go perpendicular to the plane. So that's why it's really important to think of, whenever we're thinking of a surface, we think of a normal direction n cap. Okay, so n cap is the normal direction n cap. So n cap signifies the normal direction. Okay, and how do we calculate a normal direction? And I believe some of this might have been covered in your math methods course. If not, let's just to recap this. If I have a function f, which is the equation of that surface, then the normal direction is given by plus minus gradient of f by mod of gradient of f. Okay, don't worry about this. If you have not seen this before, you will get used to this in the course. To calculate the normal, you take the gradient of the function capital F, which is the equation of the surface, and then you take the magnitude and sort of make it a normalized vector, unit vector. Okay? And n is a unit vector, so that's why you divide by the magnitude of the vector. Make sure the magnitude is 1. So let's take this example. Now my example for the equation of that surface of that line that I drew is x plus y minus r. That's my f, because that's the equation of the surface. So for that line, my equation f is simply now x plus y minus r is equal to 0. Okay. So we don't really care about 0 because this is my equation of the surface, x plus y minus r. So you take everything on one side, say that's my equation, x plus y minus r. I'll take the gradient now of f. So again, gradient is first take a derivative in x. Taking the derivative of x plus y minus r with respect to x, you just get 1, right? 1 ex plus 1 ey, that's it, and there is no z, right? So take, again, remember gradient of f is del by del f by del x ex, del f by del y ey, is del f by del z ez. Okay, so I'm just taking a derivative with respect to x, which is 1, derivative with respect to y, which is 1, into derivative with respect to z. It's ex plus ey. And what is the magnitude of gradient of f? It's root 2, right? 1 square plus 1 square plus 0 square, square root. That's square root of 2. Perfect. So now the n cap becomes gradient of f by magnitude of gradient of f, which is ex plus ey by square root of 2 and plus minus. Okay. So I've just taken the math. Don't worry about too much about this. If you're a little uncomfortable with this vector stuff, don't worry, you will pick it up. There will be plenty of opportunities to kind of get comfortable with this. But basically, write the equation of that surface, take the gradient, normalize the gradient with magnitude, you get the normal to that surface. So we get this now. The next question is, should we choose a plus or should we choose a minus? So any thoughts on that? Does it matters, or do you think it doesn't matter, or we should just pick what we like, or follow some sort of convention, or any thoughts on that? Right? You should choose to dictate. Yeah. So very good suggestion. The idea is that physical motivation should drive. Should drive. So we should expect the heat flux to flow from one direction to the other, and that could help us choose the right norm. And that's definitely correct answer to it. The way to think about it. If you are like me and you're lazy, you're like, I don't care. I'll choose any sign, and the math should just give you a negative answer in terms of the math. So that's the other option, is that you choose the other sign, saying I don't care, I will just choose a sign, and if the heat flux is in the opposite direction, I'll just get a negative in terms of the math. Okay, so let's try to see that, and we can convince ourselves. So you're saying, well, we know that the flux is radially going inwards, right? So I'll say like I'll take the positive sign. I'll still say I'll take the positive sign. I'll say normal is. So I'll say arbitrarily choose positive. Okay, so there is no logic to this. I'm arbitrarily choosing positive. Okay, choose positive. N cap is EX plus EY by square root. Okay. So that's the first thing. The question was, how do we find flux normal to this line, plus y equal to R? We first said, well, before we even do anything, we should know what the normal is. How do we define that surface? So that's what we have done till now. So I just want to kind of going back a little bit. Remember, the question is, you have been given a temperature profile. You know the flux value, which is this, which we all calculated. The question is, what will happen to the flux through this line x plus y is equal to R? So we said before we do that, we will first say what's a normal. And to do the normal, we did this calculation. We got to this answer. We arbitrarily chose the positive sign. Okay, so that's what we have done until now. So now how do we calculate this flux? And the answer is, and some of you can physically think about this, is you will take the projection of the flux onto that normal. Okay, so remember what that projection is. We said a vector can have two parts. One is parallel to that vector and perpendicular to that vector, right? If I've already found the normal, I just want to project the value to that, because anything which is perpendicular to the normal becomes parallel to the surface, right? If it's parallel to the normal, it's parallel. And if it's perpendicular to the normal, that becomes parallel to the surface. So I don't really care about it. I just want to find the component of the flux that is aligned with the normal of the surface. I don't really care about the other part. That's why you take a projection with an n cap. And note that this is the magnitude. This is simply the magnitude, because a dot of two vectors gives you the magnitude, and the direction would be n cap. The direction would be n cap. Okay. So the flux through the surface. So flux through the surface, thus surface becomes q dot n, sorry, qn n cap, or q dotted with n cap. Okay, so this is the magnitude, and this is the direction. Okay, so I know this is a little bit certain point, but I hope you can see this. This is taking the component of the total flux to that normal, and then saying this is the magnitude, and then just adding the direction to it, because we have already found it. Okay. Any questions on this? Does it make sense? Anything confusing here? All right. So we know what the Q is. So let's now do this. Qn n cap. So Qn n cap. So we have Q was minus 2K into T2 minus T1 by R square XEX plus YEY. Right? Don't forget this. This was our Q. N cap is EX plus EY by square root of 2 times EX plus EY. Or let's just read this as N cap to keep things a little easy right now. N cap. Okay. This is the magnitude. Now this comes out to be minus 2k T2 minus T1 by R square into X plus Y by square root of 2. Okay. Simply just take dot products means you just multiply the term EX with EX, EY by EY, and you just multiply the terms and the denominator becomes square root of 2. And what is X plus Y? Anybody? What is X plus Y on that line? R, right? We have been given that X plus Y is equal to R on that line. So this is equal to R. So this becomes minus 2k into T2 minus T1 by R n cap. Okay. Does everybody see the whole picture here now? Thanks. Right. This is square root of 2 because 1 square root of 2 gets cancelled with the denominator. Thanks. The square root of 2 here times T n cap. Now remember that for the n cap we had chosen a positive sign, right? We said I'll arbitrarily choose the positive sign because I just find it simpler. So I had the line like this. So this was X plus Y is equal to R. Let's just do it here. This was X plus Y is equal to R. And then the direction of the normal we chose was the positive EX by square root of 2. Okay? That's what the direction we chose. If I had chosen the negative, it would have been pointing the other direction. Okay? This is times to the positive. Do you see how this makes sense? Because now it's saying if I look into that direction, if P2 is greater than P1, this number is negative, right? So that means that heat is flowing opposite to the direction of the normal. For the negative end, right? Because this number comes out to be negative. Does everybody see that idea? That if P2 is greater than P1, then this magnitude is negative. So the value of the flux is actually the negative end direction, right? Which means it's the opposite end. So if you had chosen the other sign, if you had chosen the end to the negative minus EX minus EY square root 2, this number would have automatically become positive. So if you can choose either direction, it doesn't matter. At the end of the day, you will get the right answer as long as you just stick to one end cap, either positive or negative. Any questions on this? I saw some confused faces. I just want to make sure everybody's following this end cap idea. Okay. You can choose any other direction. It will be fine. Okay. All right. So one thing that you should try at home, and then I'll give you a break. I know it's not too much time left, but I'll still give you a break. One thing you should try at home, or rather, let's say practice. Find flux at the boundary now, and the boundary, which means your F would be X square plus Y square minus R square. Okay, so do the same thing. Find the flux at the boundary. First find the normal, take the dot product, and get the flux to the surface, and then you will be able to convince yourself what the flux is. And the answer is, it's a nice answer. You will kind of physically see what's what it would make sense. Okay? So try this at home. And so right now it's 12:59. So let's come back at 1:05, and then we finish the second part, cover the second part. Okay. I've been happy to take any questions in the meantime. Let's take a break until 1:05. Yeah, please go ahead. It's just saying that the same bar is the direction of the caps are referred to as, and you always find vectors should have a R at the bottom. Yes. I've seen it. So when I'm thinking of flux, I'm always thinking of flux across that plane, right? So let's say if I get flux parallel to the plane, that's not going across that surface. So whenever we think of flux, think of it as something going perpendicular to that surface. That's what the norm is. So it's because flux is by definition always non-normal. Yeah. You can never have heat flowing through a surface in the parallel direction. And what about so yeah, so basically any vector, right? Let's say we have this here. Let's say I can always take it down to normal. And this will be minus normal vector to the parallel. So you will always break down either tangential or not. Either tangential or not. Cannot have either direction. Yeah, so always break down the normal part. Yes. Yeah. Yeah. Really. Yeah. Such that we can build absolutely yes. The is basically making everything equal to zero. I got a question. Yeah, if you ask me after the one. All right, let's maybe start again. So just a refresher over the last 1 hour or so, what we were discussing was heat conduction. We learned about Fourier's law, we learned about gradient, how to take the gradient, and this last topic we were discussing before we ended was how to take flux across a surface. We create a dummy function f, take a gradient, normalize by the gradient to get a normal vector, and then take a dot product of the flux with that normal vector to get the flux across that surface. Okay. And there was a good question during the break was that flux by definition is actually always going to be normal. You can never have flux across a surface and then say it's also parallel to the surface. So always remember, flux is always across the surface, which is why it is always going to be normal to the surface, and which is why you put the normal component. Okay. So what I want to do the remaining 15 minutes is kind of introduce this topic of species diffusion. This is a slightly more subtle topic and complex topic than heat conduction, but as you will see as we progress in the course, that they have a lot of similarities in this way. Okay, so let's start again visualizing what a model system could be. So for the heat conduction, we thought of a iron rod which is hot, from one point temperature is higher than the other. For species diffusion, I wanted to think of something like a water pipe. Let's say something has water here, and let's say at one side we are dissolving gas. Okay, so dissolving gas, it can be any components. So there's I components, and the components can be like dissolved carbon dioxide, dissolved ammonia, oxygen, and so on. Okay, so think of that at one side I've dissolved some sort of gases in liquid. So what I'm really trying to do is trying to think of that species in the liquid, the dissolved carbon dioxide, ammonia, nitrogen, so on, and that it's only dissolving on one side, so the other side is free of that gas. There will be a concentration difference now. In the first part was a temperature difference. Here now there is a concentration difference. Okay? So that's what we have to think about species diffusion. Like a species is diffusing. Now I will write a bunch of mathematical equations which are trying to kind of construct an idea of this diffusion. Just stay patient, they're a little bit more complex and can be sometimes confusing. So I'll try to clarify, but let's just start to write down some equations and then I'll try to construct and sort of try to understand what's going on. Okay. So I'm writing small ni, which is equal to CIV plus J of I. Okay. And this is also equal to, sorry, my mistake. This is rho I, not CI. Rho I of V plus Ji is also equal to rho I of V of M plus Ji of M. And then I have this capital N of I, Ci of V, capital J of I, Ci V of M plus capital Ji of M. Okay. So just write down, I'll explain every single term, we'll go through them and then make it. Okay. So what we are trying to do here is trying to represent the flux of the ith species. So think of flux of the dissolved carbon dioxide, flux of the dissolved oxygen, flux of the dissolved ammonia, and so on. This is the flux of the ith species. So what are the units of the flux? If I have small n, small ni has the units of kg meters per meter square second, is the mass flux. Okay. If I have capital N, that's the molar flux, mole per meter square second. Okay. Mole per meter square second. First, left hand side are simply the mass and molar flux of the ion, which is the dissolved carbon dioxide, dissolved ammonia, dissolved oxygen. Now, can anyone tell me if there is a relationship between the mass flux and the molar flux of any species? Can we relate them? How can we relate them? Molar mass, right? So they are not independent. These equations are not independent of each other. We know that we can go from mass to moles by using the molar mass. Okay. So if I have capital N of Ni, that is small ni by Mi is the molar mass, and the units being kg per mole. Okay. So we'll take 1 mole, we'll try to find how many kgs are there, and then we'll just divide by this to convert from kg per meter square second to mole per meter square second. Okay. So that is a way to connect the molar mass flux to the molar flux. Okay. Is that clear to everyone? Just the left hand side right now. We are not going to the right hand side. Go there. Okay. So the left hand side is simply the mass flux or the molar flux divided by the molecular mass. You can convert between the two. Now, what are all these things that I have written? We didn't have any of this when we were thinking of the heat flux. So this is very crucial to understand, and I've seen over the years, this is the part students get most confused part, is that when we are thinking of diffusion, and it's like several species in the system, you have to think this first part is sort of like the convective or the mean motion. Okay, so think of it as the mean motion of all the species combined, mean motion. Okay, and deviation from that is the diffusive motion of the species. So this part is the diffusive motion. So the left hand side is the total flux. I can break down that total flux into the mean motion plus the diffusive motion. Okay, so that's the point. We have two of these sort of like mean motion or sort of the average motion plus a diffusive component. So that's the first part. So small j is a diffusive flux. So now let's start to expand our definition. So Ji is a diffusive flux, and it's not the complete definition. I will complete the definition in a second. It also has the units of kg per meter square second. Rho I is the density of the ith species. Density of the ith species. And that has the units of kg per meter cube. And velocity v vector is the mass averaged velocity. This is super important. What is this? Mass average velocity, and has the units of meter per second. Let me highlight, this is the mass averaged velocity. Okay, mass average velocity. So what's going on here? I'm saying that, so you can also see if some of you are confused, this density times velocity is going to be kg per meter square second. Okay, so density times velocity gives you units of diffusion. It's saying that all my species, let's say if I have any of the species, they're all moving with some velocity v. Okay, there's some mean motion of velocity v. I multiply by their own density, I get the mass per second. Okay, so that's the mean motion, and Ji is the deviation from that motion. So that's the total flux. All the species are moving with the same velocity v. Now, but you see on top, I have two definitions. I am breaking down that flux in two different ways. In one case, I am saying velocity v is the mass average velocity, and now I will define Vm, that is the molar average velocity. And I will describe why there is a difference between the two. Okay, so I'll describe it in a second. But I hope you can see, basically you're breaking down the flux into two parts. One is the mean motion and the diffusive motion. And when we break down, when we define the mean, we need the velocity. And when I define that velocity, I'm saying a mass average velocity or a molar average velocity. So this Ji definition is not complete yet. It is based on mass averaged velocity. Based on mass average velocity. Then I can also define Ji of m is also the diffusive flux, but based on molar average velocity. Sorry, based molar average velocity. And V of m is the molar averaged velocity. This also has the units of kg per meter squared second. Sorry, kg per meter squared second. And Vm has the units of meter per second. Okay. So I hope I understand this is a little bit, sometimes seems like a little bit twisted concept, but it will become clear with time. But the point being that we have a total flux small n, we divide it into two parts. One is the mean average velocity times the density. Then you have the diffusive part, but how you define the velocity would be either the mass-based velocity or the molar-based velocity. Okay? So that's the part. Now, at this point, do you see that there are another thing? I now have a capital Ji and a capital Jim. The two variables I have not defined, and there is a Ci and Ci which is also not defined. So let's define them also. So let's define CI. CI is the concentration of ith species. Concentration of ith species, and that has the units of mole per meter cube. So many of you must have seen this molar, right? Moles definition, mole per meter cube. Capital Ji is diffusive flux based on mass average velocity has the units of mole per meter square second. Ji of capital M is diffusive flux based on molar average velocity. Molar averaged velocity also has the units of mole per meter square second. Okay, it's a lot to take, I realize that. So let's try to think of this and reason out. Hopefully I can push this here. Hopefully, yeah, all the definitions are here now. So can someone tell me the difference between small ji and capital Ji? What is the difference between small ji and capital Ji? I have said that both diffusive flux based on mass average velocity. What's the difference? So small ji and capital Ji. In the units, right? So the units of small ji are the kg per meter square second, and the units of capital Ji are mole per meter square second. But I can go from one or the other by using the molar mass, right? So basically, I can go from one to the other by using the molar mass, or you can think of this as this is simply Ji. This is Ji by Mi. Ji by Mi. Just make sure I write the vector correctly. Ji by Mi, and this is Ji molar by Mi. Okay, so I hope you can see that basically it's the same vector but expressed in different units. Okay, so there are two parts. One is the unit of the flux, and one is what is the velocity, whether it's a molar average velocity or a mass average velocity. So some people call it capital Ji to be mass flux based on mass average velocity. Ji of M to be mass diffusive flux based on molar average velocity. Okay, so you can have sort of like these four combinations: Ji of M, capital Ji, capital Ji. Okay, so that's the definition. Now let's just last two formulas before we wrap up the lecture today. Is that what is this V of M and Vi of M? So what is V of M? V and Vi of M. So maybe let me just back up a second. I want to go make sure everybody can see this. Okay, so we have this as a definition of M. Now take summation. Take summation. The summation of Ni is some V is common, so it becomes summation of rho I plus summation of Ji. Okay, so the sum over all the species. Now, what do you think is the summation of small ji? Any thoughts, any ideas? What do we think is the summation of small ji? Zero, right? Because if I'm summing all the fluxes, there cannot be any variation. It is a definition. So this will go away. So small ji goes away. Small ji goes away. And the velocity definition becomes summation of Ni by summation of rho I, or summation of Ni by rho. So where rho is defined as the summation of rho I. Out of just for completeness, I will write the formula, but we'll discuss this again in the next class. Molar average velocity is called summation of capital Ni by summation of Ci, or summation of capital Ni by C, or where C is summation of total concentration, summation of Ci. Okay, so basically definition of V is sum all the mass flux divide by all the summation of the density, you get the net molar average or mass average velocity. To get the molar average velocity, sum all the molar fluxes and divide by the concentration of the molar average. So that's the definition. They are not the same. Molar average velocity is based on the molar fluxes of some of the molar fluxes, and the mass average velocity is based on the mass. And you might be wondering why to make all this mess, why to confuse ourselves by having all these weird definitions. And the answer is that in some cases, actually this definition is more helpful, but in 99% of the cases, B is the most helpful, which is probably what we're more familiar with in the undergrad courses, the top definition. But this definition can be useful, especially in gas diffusion problems. So if some of you are going to do catalysis, you may have a gaseous system, it is the molar average velocity that might be. Okay, so we'll discuss that in the next lecture. And I'll again walk through over this entire Fisher diffusion again. We'll define fixed law and go on. Okay, I'll be available to meet for office hours if anybody has questions. And then we'll meet on Wednesday. Okay, and we'll post the homework on Wednesday as well.